you're in one of the biggest universities in the country now, and one of the biggest chemistry departments in Europe really, is the one that I work for in Manchester. And this particular lecture is named in memory of a former colleague of mine, Dr John Salthouse. When I was a bit younger, I had the pleasure of seeing one of these demonstration lectures given by Dr John Salthouse. He's quite a well-known name, even worldwide, in fact. He had quite a reputation, and little did I know when I was sitting watching that show that I'd end up doing those very same demonstrations. So, without any further ado, I think we can move on into the first demonstrations, which actually are not going to be explosions. I've got some potassium iodide and some lead salt here, and when I combine these two, we're going to get a pretty fast reaction. And as soon as that goes in there, I get a nice bright yellow colour. And the fact that we live in a bright colourful world, and we've got purple seats and red lasers and all that, we've got chemists to thank for that. That was an example of quite a fast reaction because both of those solutions were quite concentrated with quite a lot of stuff in them, which meant there was lots of collisions very fast between them. If we use more dilute solutions, then it takes a little longer for the right species to find each other and bump into each other. So if we put that one in there, nothing much happens. Then if I put this one in there, we get a little bit of an orange coloration. Is this going to do its thing for us? Yes, it is. We get a blue coloration. So that shows you that sometimes reactions are a little bit slower. We use more dilute solutions. This particular reaction will get another trick under its sleeve, because we can actually take it back to the beginning again, and it will go colourless, and then it will go orange, and then it will go blue. So in here I've got my special liquid. It's mainly water, but it's got something else in it. Also made of hydrogen and oxygen. I'm sure you all know that water is H2O. Yes? Does anybody know what the chemical formula for hydrogen peroxide is?
H2O2.
H2O2. So this chemical is fundamentally, would rather be H2O. And we've got, but the oxygen atoms are chemically bonded into the other parts of the molecule, so it can get out. Not just yet, it can get out and form oxygen gas. Now, to form oxygen gas, how many atoms of oxygen are we going to need? And there? Yeah. 2. Good. There's 150 mils of this H2O2. But here, the oxygen atoms are bound and they are in the liquid state. So in the liquid, the molecules are reasonably tightly packed. They were pretty much, as you come into the lecture theatre here, all quite packed. You can still move past each other, but that was pretty much what a liquid was like. The molecules are quite tightly packed, but they can just still move past each other, so they can take the shape of the container, etc. So that's what it was like. And contrast that to the situation when we get oxygen into the gas phase, because oxygen is going to exist normally as a gas. Some of it will dissolve, but a lot of it's going to come out. So we're going to try and catch that oxygen gas as bubbles, and we'll do so because we've added some washing up liquid there to catch it as the bubbles. Now, all we need to do, so we can use a catalyst that gives a very ready route to lose its oxygen atom, and that catalyst in this case is potassium iodide. So if we put that in there, we see that the oxygen is formed, you get the bubbles, and there is an awful lot bigger volume of bubbles than there was of the original liquid. We're going to put some dry ice in and we're going to get bubbles and we're going to get clouds, but I want to focus on something else, which is the fact that we've got a colour here, a nice purple colour. What happens, because it's purple because it's got universal indicator in it and it's got potassium hydroxide, so it's a strong alkali in there. You've learned about universal indicator, you'll recognise that colour, I guess. You'll need to learn these colours for your GCSE. So as the dry ice goes in, some of it will dissolve in the liquid, and that will react with the potassium hydroxide, and so the pH will change eventually, and I think it's starting to go blue now. So we're going to go to sort of grey colour, and then it's going to go blue, and then it will go turquoise, and then it will go green. And I think, yeah, it's on its way to yellow already, so now it's neutral, and I'll put a bit extra in. We should get it to orange. bit. More and more of the carbon dioxide is going in, it's reacting with the water and producing carbonic acid. So what that shows, we started with a strong alkali, and now we've got a dilute acid, a weak acid. And the final thing I need to get it to burn is a fuel. So the fuel I've got in there is icing sugar, same fuel as you and I might use, sucrose, sugar. So let's have the lights off, please, and we'll see what the potassium plate looks like. Like that. So that's a lilac plate. Like you'll recognise this shade from street lights at night because they rely on excited sodium ions. So lights down, please. So there's orange, see that street light orange? And so we've now got a mixture of CS2 and NO. And if we have the lights completely off, please, this will generate its own light. Incidentally, that process where you make a molecule which has got too much energy and it then gets rid of the energy in the form of light has a special name. It's called chemiluminescence. So firefly is an example of a chemiluminescence phenomenon. This is the most intense, fastest chemiluminescence you'll ever see. So this is like a glow stick. Glow sticks you're familiar with, those plastic sticks you can buy. You crack them and shake them and you get light coming out. That's a chemiluminescent reaction. You crack them and shake them, makes a chemical reaction, produces a product with too much energy, gets rid of its excess energy as light, and it glows for a while. This one just very, very short and intense. Live fast, die young. So, lights please. Thank you. Oops. If I was to burn it in the air, it struggles a bit. It just about burns, but eventually it will give up. We don't have to put up with that because we are chemists. I could take that nitric acid that I made there and react it with the cellulose that the cotton is made of, and that would give me this stuff, which is nitrated cellulose. And looks like cotton wool. It started as cotton wool, but we've done chemistry on it. We put nitro groups on it, NO3, right next to where the fuel is, so it burns a bit faster. That's called flash cotton. Try that cotton wool again. It was a bit rubbish on its own until we nitrated it. But if we put some in there and soak it in neat oxygen, even though it's freezing cold and sopping wet. Okay, what does that look like then? If we set lights in that, keep the lights up for this. And we use Dr Salthouse's spoon, memory of him. This is one of his favourites. So here in this cotton wool plus liquid oxygen.
Whoa!
Alcohols, which are renewable fuels. Mix the alcohols with some borates, and this will give us lights down please for this one. Just a push, not a bang.